So as promised, we're going to start with the mini tutorial on how to use DMSwarm, this object that helps us do particles with fields together. And following that, we'll have some talks that follow up on the mini tutorial that we had yesterday from Hongzhang on DM Network. But first, here we have Joe again for DMSwarm. Thanks, Joe.
Thanks. So, like any of the other DM objects in PETSc, DMSwarm's goal is to provide parallel data management. So what changes basically is just what kind of data we're actually trying to manage. And then click got it, yeah. Oh, but my cursor's gone. Can I click enter? No. No. Oh, okay, got it back. Cool. Oh, no worries. All right, so parallel particle management for particle discretizations and for PIC discretizations so that we can have a way to easily store user data that they want to discretize via the particles and interact via the rest of PETSc. So if you want to do something like particle and cell discretization, which we have here, which is an example of the two-stream instability problem in plasma physics. It's a very classic problem looked at since the 1950s, 1960s, and is one of the first problems you encounter in the introductory plasma computer simulation textbook from like the 1980s, Birdsall. You have two beams of particles overlaid on one another with opposing velocities, and you just let these particles go, but the beams themselves are unstable. They have the same velocities in each direction, but the instability of this beam grows in phase space, and we get this phase space vortex that forms and just persists and sits there until it destabilizes and just kind of eventually starts to thermalize if your regime is in the right place, right? So I'm going to talk about how we build up something, simulation like this, and then give just a very basic high-level overview of how you can actually start using this data structure, because it doesn't necessarily look exactly like other DMs within PETSc. That's something I'm currently working on right now to start bringing this in so that all your APIs kind of look similar and you can interact with it in the same way that you would interact with, say, a DMPlex, right? So I asked myself, what was the most boring possible representation I could pick for a particle discretization? And this wasn't it, but it was a runner-up. So some collection of particles that we have laid out on the grid, and the DMSwarm is going to provide you all the data structures and particle discretization tools that you need to start pushing these particles around, having them interact. You know, particle pushes via TS, parallel communication via DMSwarm migrate, support to work alongside structured and unstructured grids with DMDA and DMPlex. So you can do like an FD discretization or a finite element discretization, and being able to track where these particles actually are within my grid via a point cell location with a DA bounding box, or some of the different ones that DMPlex supports as well. All right. So high-level internals, what makes up the swarm? It's definitely good to understand what's going on in the internals as you move forward so that you understand what's actually happening when you go through and make these API calls. So at the core of the swarm, we have the DMSwarm data bucket, which is going to store all the predefined fields, something like a DMSwarm pick field, so you have a coordinate automatically defined on the space that you're setting up your swarm to work with, as well as a cell ID and a rank, so that you can use that when you're doing your parallel communication. If you want to define your own user parallel communication scheme, you are free to do that. Give it to the swarm and the swarm will use it. And you can define your own swarm fields, like if you have a particle that needs to represent some kinematics, such as a velocity, a weight given to it. It can represent the pressure at a given point, and so on. So they're really highly configurable. It just takes the configuration to get to that point and knowing what calls you might want to make to get there that may or may not be inherently obvious when you just look at the documentation page and it's like, oh, register field. Well, that just gives you, you know, your own user-defined information or topology that you want the swarm to be able to track. So then at the next level, the parallel part of the parallel particle management is the DMSwarm migrate function. If you're doing parallel simulations with it, that's something that you'll use a lot. So I want to touch on that as well. So that's built up of point cell locations, so understanding whether or not the particles belong to me. So is the particle located within the bounding box that my rank has been assigned, right? Something like a Poisson problem where I showed that these particles are moving in phase space constantly. If I have my phase space discretized and distributed amongst various processors, then I need to push them to those processors. So is it within my domain? No, mark it, send it to my neighboring processor, and my neighboring processor can decide if it's within its domain, and if so, keep it. If not, get rid of it. You don't need it. Right, and then that is encapsulated within the DMSwarm data exchange object. Not really an object, but that data exchange will perform all of your array packing and everything for you, so that when you, for migrate too, so that when you call migrate or when you're trying to actually communicate these particles amongst different ranks, the data exchange will figure out how big the arrays need to be, pack the array in there, and send it via MPI. Right, and then you can also have your auxiliary information like your cell DM if you want swarm pick, so that you can manage your field particle interactions via like finite elements, and then interpolate your fields to the particle coordinates, give it a push, and then write that back to the DMSwarm, and then your problem will evolve that way. Right, so how this kind of looks, we have our data bucket, cell DM, and then our collection of algorithms, which is the really super useful part alongside all these interactions it can have with the different PETSc types. So algorithms for point cell location via the plex, algorithms for inserting particle coordinates, tracking what's called a swarm sort context, so that if you're working on the swarm and you're trying to figure out like how many points are in a given cell, and you want to operate based on that number of points, knowing that that's still valid when you're actually carrying out these operations on the swarm. So that context will get invalidated if you corrupt it, and then your operations won't be able to proceed. So some simple protections and some error checking within your particle migrations and whatnot. So the swarm can also interact via TS. You can give the TS a DMSwarm the same way that you would give a TS any other DM. And from there, the DMSwarm has different ways that you can interact with the TS and your SNES objects and your different solvers. So you would, like I said, it doesn't necessarily behave directly like other DMs. So like DMPlex, it can just do get vector and it'll give you the vector, but for a swarm you need to tell it like this field in my swarm defines the vector. So you can have different data representations on each particle, say that I have a coordinate space, I have a velocity space, and then I have a weight. Obviously they're of different sizes, so you need to tell the swarm which field it's going to give back so it can actually appropriately define the vector that it needs to give to, say, form a Jacobian matrix that's going to be used for storing Jacobian computations in. All right, so I want to give just a basic top-level overview of what this actually looks like in code. So same way you would any other DM, DM create, set the type to DM swarm, give it a dimension, and if you want swarm pick, do set type DM swarm swarm pick, and then DM swarm set cell DM. So that tells the DM swarm what what it's actually going to use as its backend. So it'll make a switch between some of the things it wants to do based on whether or not you've got a structured or unstructured grid. So DMPlex, DMDA. Right, so those are supported separately in their own implementations. So once you actually generate your swarm, if you want to have your own customized swarm and you don't just want something that has particles that only have coordinates, you can register these as DMSwarm register PETSc data type fields. So you give it the swarm, give it a name, tell it how many entries that it's actually going to have per particle. So velocity, you would give it something like the dimension of the problem, a weight, or a species. You can just do index tracking and then tell it the PETSc data type that it's actually going to need to size the arrays for that it's going to store these in. So PETSc int, PETSc scalar, PETSc real. Yeah, I don't know why I have PETSc scalar there, because DMSwarm right now only works for non-complex builds of PETSc, just so you know. Right. So once I have these fields defined, how do I get, interact, and set these fields? DMSwarm get field, so you give it a name. You notice that DMSwarm pick field core is a little bit different than something like WQ, representing the particle weights. That's because weights are user-defined. DMSwarm pick field core is built right into DMSwarm, so you can get these fields directly out of it. Give it an array, and then start doing like your computations based on your problem topology that way. So here we just get the centroid of the cell and assign the coordinates to be the centroid of each cell, which is what this loop is doing. So C equals 0 is the 0 cell, and then the number of cells, loop through them, assume we have 1 particle per cell here, and then assign the coordinates to be the centroids, right? Now, before we get there, we want to look at how we actually configure the sizes of the swarm itself, right? So there's 2 options. One way is to go through the options database. You can see here like DMSwarm num particles tells it the number of particles that you're trying to allocate for. Give it a coordinate density, so it'll initialize your particle coordinates to whatever kind of function you want it to. You can define your own function and give it to it that way. We have some predefined functions like constant and Gaussian. I'll talk more about the Gaussian in a second because you need something else for that too. The number of particle species that you want, so it'll go through and allocate the species field for you and start populating based on separate distributions for different particle species, and then tell it how you want a velocity function defined, and it'll go through and allocate based on how many particles you've defined and what you want your velocity distribution function to be. The other more classic way to do this is you just finalize your field register, so you define all your fields that you want. You say we're working with a plex, so I get the number of cells, and then DMSwarm set local sizes, so it'll allocate the size of the swarm, so the number of particles that you have and that you're storing, it'll allocate all the data types for you on the local rank, and then just set from options to get some additional DM type options on your swarm. Right, so how do we get things in and out of it? Aside from working directly with our fields and getting arrays back and forth, we can get PETSc vec objects, which then I'll have all the PETSc vec backends if you're defining them appropriately. Give it the swarm, give it the field name, give it the vec, and it'll give you either a global or local vector back that you can then work with, obviously, in between here before you destroy the vector itself. So say we go through and we get some particle pushes going on, evolving something with a time stepper or a SNES solve. My swarm has changed, might be outside the domain, and I want to start pushing particles around. DMSwarm migrate is the API call that you want to do that. There are some command line options for the swarm that I'm currently merging in that are going to allow you to change the type of migration algorithm that you use to perform migration. So the way it's set up right now is to do something called a DM cell neighbor scatter, where it's going to go through, get all of its neighbors from PETSc and then communicate the particles directly to its neighbors. I'm working in an all-to-all type communication scheme at the moment. You just wouldn't typically see that in the type of work that we've done so far where you're skipping entire ranks worth of domains. So I'm just working to get that support in right now. So let's say you did something like initialize everything on rank 0 and then I want to broadcast all the way over to the other side, that you might lose some particles trying to do that. It's just not supported at the moment, but it should be soon. And then, as I mentioned, our DMSwarm sort context, so I want to protect the swarm while I'm working with the swarm and make sure that nothing's corrupted. I'm not gathering neighboring indices that I shouldn't be gathering. So DMSwarm sort get access. That's going to give you access to all of these DMSwarm sort context type API calls, so like DMSwarm get points per cell. It wants to make sure that you didn't corrupt the number of points that actually exist within that cell while you have that swarm sort access. And then, do something with based on the number of particles that you have locally, and then give the access back. So you can see a lot of different functionality can be built up out of this very, I want to say, simple API. And we can start to construct some different solves with our particle discretizations. So here's a location for some of the different DMSwarm tests. These aren't necessarily tutorials themselves, but they do serve the purpose as teaching how to do things. So if you want to look at some of these, feel free to check them out. So source DM impulse swarm test EX1, that's a test I'm actively working on right now for the new particle migration and point cell location algorithms we're developing, and then the conservative projection operator that I showed in my talk earlier, that's in impulse swarm test EX2, so that'll show you how to project your fields directly into a finite element space and then project back to my particle space and compare the moments of the discretizations. Example 3, subswarm, so I can pull a cell out of the swarm and have it be its own DM swarm. And then some other examples that include like Kolmogorov-Smirnov tests and Gaussian initialization and so on. And then two-stream instability is Hamiltonian example 2 inside TS. So hopefully that was somewhat useful. Thank you.